Swayam Prabha. Digital India. Educated India.
Hello, welcome to this course on transport phenomena. This is lecture 19, and now we are talking about heat transfer. And in the last lecture, we finished conduction heat transfer, and now we have started convection heat transfer. And in the beginning, we are discussing about the physical mechanism of convection heat transfer and how do we analyze heat transfer problem. So far, we have realized that that the formation of there is similar to the formation of velocity boundary layer in the fluid flow. There is the formation of thermal boundary layer in heat transfer, and that is very important for our analysis. Okay, going forward. We'll further discuss about the effect of boundary layer on convection heat transfer coefficient, and we'll also develop our understanding on how to analyze these convection heat transfer type problems. Okay, so we have seen that the convection heat transfer coefficient can be given by this equation. H is minus kf, where dou t by dou y at y equals 0 represent the temperature gradient at the solid fluid interface. So if you have a heat transfer fluid flowing over a flat plate, something like this, then the temperature gradient at over this surface at any location x, h is we have seen that h is also a function of x. So it can be given by this equation. So now what we are going to talk today are these things. So laminar and what happens to thermal boundary layers when your flow is laminar, and then the transition happens to turbulent flow. We'll also talk about boundary layer equations. We will not go in detail about how to solve these equations, but we'll do some analysis to see how these equations are related across different transport processes, like momentum transport or thermal transport or mass transport. We'll look at the functional form of solutions, something similar to what we did with friction factor, and then we'll talk about boundary layer analogy, and finally we'll start this example of convection by discussing about external force convection, that is flow over a flat plate. Okay, so between two, when you have a laminar versus turbulent, if we look at the velocity gradient, laminar versus turbulent. So if you have let us say this is your plate. Okay, you have fluid flowing over here. Yeah. So as we know, there is some boundary layer development, and if the flow is laminar, then we can. So till the point it becomes the velocity becomes 0.99 of v infinity is your boundary layer. So if this is your boundary layer thickness, maybe something like this. Okay. So at this point, your v is 0.99 times v infinity. Okay. In comparison to that, when you have a turbulent boundary layer, what happens is that you have a significant mixing, right? So if you here you can define layers of fluid flow. In the case of turbulent flow, rather you have vortex formation and eddies and all those things. So you have a lot of mixing, right? And so on. Yeah. So because of that mixing, because of that mixing, the velocity changes very, very fast close to the plate. At the plate, it has to be 0 because of no slip condition. So it suddenly becomes like this. The boundary layer thickness still increases because of this mixing. The slower fluid packets are also getting mixed to the bulk. So the effect of this friction is felt even in the farther in the bulk. So because of that, the boundary layer thickness increases, but at the same time, close to this interface, you still have the close to this interface, you will have very steep gradient in velocity. Okay, so in this case, your velocity profile will look like this. Immediately it goes to higher velocity because of this strong mixing. Okay, so when this happens, that also affects your heat transfer. So what will happen essentially is, if you try to plot heat transfer coefficient with h with respect to your x, so flow starts initially in boundary layer flow is laminar. So h decreases with x, that we have seen in last lecture, right? H decreases with x because boundary layer thickness grows, and your temperature is here it is fixed at Ts, here it is fixed at T infinity. So as the thickness grows, that dou T by dou Y will also decrease. Okay, so that is why your H decreases. Now, when you have transition, that is in the transition region, that flow can be sometimes laminar, sometimes turbulent. So it has some mixed behavior. So in this case, what will happen is actually no, we don't know what it will be. So let us show it as dash line. Okay. In turbulent regime, because you have very strong mixing, so colder fluid from here can be easily taken away from the surface. So there will be strong mixing. So you can see that there will be more efficient heat transfer when you have turbulent flow. So again, your what will happen is essentially your heat transfer will suddenly, after this transient region, when flow is turbulent, your heat transfer coefficient will increase, and then it again decreases because your boundary layer thickness keeps increasing. Okay, so this is your this is laminar region. This is your transition. Okay, and then here onwards you have turbulent. Okay, so that's the difference between laminar and turbulent conditions. Okay, we can also say that in the turbulent regime, if you want to compare the thickness of velocity boundary layer versus this is your velocity boundary layer, this is your thermal boundary layer, delta minus delta T, then laminar regime, it will depend on what kind of fluid you have and so on. But in turbulent regime, it should be almost same, because in turbulent regime, the heat transfer is actually governed by fluid flow, because you form because the flow is turbulent, so the mixing is nice. So you have very effective heat transfer, and so the boundary layer thickness should be almost same if you have if you are in turbulent regime. Okay, so delta minus delta T is almost 0. Okay, so now let us move to what we call as boundary layer equations. Essentially, it comes from your conservation of mass, continuity equation we have seen, and we are talking about flow over flat plate, so that can be considered as two-dimensional. So you have flow over here, and then in x direction, and then in y direction. We are not concerned about the width of the plate, because that would be the similar flow. Okay, so we are concerned about flow in this direction, and then you have y. Okay, yeah. So the conservation of mass can be given by dou u by dou x plus dou v by dou y. For energy conservation, we can proceed in the similar fashion we did for the Navier-Stokes equation. In this case, what you can do is, let's say you have a boundary layer here. Within the boundary layer, we have considered our flow to be 2D. So if we consider a control volume delta x delta y times unit width, then you can consider the heat coming in minus heat going out, and if we write this at a steady state, then the accumulation term is 0. So heat coming in, heat coming out, there are 3 terms. But viscous dissipation term we can be we can ignore under certain conditions. So there will be one Q in, and Q term, that will be conduction. So conduction through this phase and this phase coming in, and this phase and this phase going out, and then you will have another term, advection, because of the bulk fluid flow. So advection term will again will be from here coming in, and then going out. So if you consider all these four terms and write the equations, and then incorporate this this continuity equation, what you will see is you will have this term. Okay, so you can relate this to Navier-Stokes, where you had mu dou v by dou x squared plus dou 2v by dou y squared, and so on. So it's related to that, and then it looks similar. And similarly, this time it's part of what we defined as substantial derivative, and this is without the time term. So you can roughly relate it to Navier-Stokes equation. I'm not going into the derivation for sake of time, and we have done similar exercise before, so there's no point in repeating it. You can do it to convince yourself that that you are able to derive this equation. Okay, so now for the given situation, what we see is the temperature from here to here changes rapidly compared to what it will change in x direction. So what we can say is dou 2t by dou x squared should be much smaller than dou 2t by dou y squared. So the change in temperature from here to here is much larger, because your boundary layer thickness is typically small. So this change is much larger compared to this change. So we can assume that. With that, the equation changes to a simpler form. So u dou t by dou x plus v dou t by dou y. Okay. Then alpha is of course your k by rho Cp. Right. Yeah. Okay. So now what we want to do is we want to non-dimensionalize this equation so that it will become more clear when we non-dimensionalize it, and then we compare it to momentum conservation equation. And the non-dimensionalization also lets allows you to use solve the equation for more general cases. We will see these things a little later. Okay, so to non-dimensionalize, we can use x star as non-dimensional dimensionless x, dimensionless y as y star equals y by L, and u star is u by v, where v you can think as v infinity, v star is v by infinity, and then to we can define a dimensionless temperature similar to what we did earlier for theta. We wrote as theta star, so T minus Ts by T infinity minus Ts. Okay. So now if we use all of this and in this equation, so what we have is initial equation is u dou t by dou x plus v dou t by dou y alpha dou 2t by dou y square. Okay. So now if we go term by term, let's do the right hand side first. Alpha dou 2t can be written as, from here you can see that t minus ts is equal to t infinity minus ts times t star. So if you differentiate both sides, this term is constant, so this will go away. So you will have dou t equals this time dou t star. Right. So we can write alpha. So this will be t infinity minus ts alpha t infinity minus ts, and then you have dou t star. Okay. And similarly, y squared will be your y star squared times L squared. So you will have L squared. Okay. Now look at let us look at LHS. U will be from here. U will be V infinity U star, and V will be V infinity V star. Okay, so you will have V infinity, and X will be, so we can write that as T star. Sorry, T star you will have to multiply T star, you have to do T infinity minus Ts, similar to what we did there. Okay, so it is a little bit. Okay, so T infinity minus Ts, that you can write as T star here, and U you can write as V infinity times U star by X star. So this will be L times X star. So now you will see that the same thing will come when you non-dimensionalize all these three things here. So we can write this as common. T infinity minus Ts will come for this. L Y star will be this, and V infinity V star will be this. So wait, we need to still do some erasing. So U star has to come inside. So it should be U star do T star by do X star plus V star do T star by do Y star. Okay. So now this would be equal to this. This would be alpha T infinity minus Ts by L square due to T star okay. So this we used all these things here to non-dimensionalize your energy equation. Okay, so now if you compare these two sides, you can cancel this. Okay, so now if you look at this right side, what you can write is just this coefficient term. L will cancel out. So the coefficient of RHS is alpha by L times V infinity. So now you can see that it's going towards, you can make some arrangement to make it Reynolds number, because Reynolds number is rho V infinity by mu. So if I multiply by rho here and to denominator and numerator, and then this is rho V infinity L, and then you have to do mu here and mu here. So now if you look at this, so rho V infinity L by mu, this is your REL. And then what is left over? Rho, this is gone. This is gone. So what you have left over is alpha rho by mu. So we can write alpha mu by rho as well. Okay. So what we can write this as 1 by REL. We know that mu by rho is your momentum diffusivity. So that's mu by alpha. Okay. So this mu by alpha is you can see that it just depends on fluid, thermophysical property of fluid. So nu by alpha is the ratio of momentum diffusivity to thermal diffusivity, and this is known as Prandtl number. So you can write this is 1 by REL PR. So with that, our final equation looks like this: U star do T star by do X star plus V star do T star by do Y star is equal to 1 by so it will be essentially 1 by REL PR and do to T star by do Y star square. Okay, so it's written again here, so don't worry about that. So this is your normalized a boundary layer equation. Similar equation can be, similar thing can be done for momentum equation as well. We are not going into detail about that, but your normalized momentum equation will look like this. So you can see that there is a good similarity between these two equations. So you have, if you solve for u star or you solve for t star, except unless, if your dp by dx, dp star by dx term is 0, then this equation is very close to this. Further, if your Prandtl number is equal to 1, so we can see that if your Prandtl number is 1, dp star by dx star is equal to 0, which is essentially saying that your pressure does not change along the length of flat plate, which is not a bad assumption. So dp star by dx star is equal to 0. If you see for these two cases, then actually these two equations are essentially same, right? So if you solve one of the equation, then you have solved the other equation. So that way, that is the that is how you can compare fluid flow and heat transfer. And similar thing happens for the mass transfer. One can write this equation in terms of concentration of a species, and you will see the similar equation. Okay. So we know that Reynolds number is ratio of viscous to inertial forces, and Prandtl number is relative effectiveness of momentum and energy transport by diffusion in the velocity and thermal boundary layer. Okay. So typically for gases, Prandtl number is equal to 1. Liquid metal, Prandtl number is much less than equal to 1, and oil Prandtl number is much greater than 1. And as we have discussed, this is depending on this relative effectiveness of momentum and energy transport, that will affect your boundary layer thickness. So delta by delta t, this is for laminar flow, is very close to, is approximately equal to Prandtl raised to n, where n is a positive number. So for example, for liquid metal, you can see that delta by delta t is much less than 1. Right? Once Prandtl is less than 1 and you raise some positive power to that, it will be less than 1. So what we see is velocity boundary layer for these cases will be much smaller than the thermal boundary layer. Why it happens is for Prandtl number much less than 1, what we see is nu is much less than alpha. So your thermal diffusivity is much faster. Since thermal diffusivity is much faster, the effect, the cooling effect, or heating effect, whatever happens here to the gases or liquid will be easily, we can transfer to larger distance in this direction, because its thermal diffusivity is much higher. Okay, and because of that reason, your thermal boundary layer will be much larger than thickness. Thermal boundary layer thickness will be much larger than your velocity boundary layer thickness. This is for liquid metal. Okay, for oil it will be just opposite. Okay, so you can see that these things are these equations, actually you can see the similarity, and then Prandtl number lets you compare two boundary layer thicknesses. Okay, so now that we have non-dimensionalized equation, we can again look for the functional form of the solution. So this is for the momentum balance equation. So you have functional form of for u star, that is the main variable in the equation, can be written as the function of x star, y star, Reynolds number, and then dp by dx. Okay, where dp by dx essentially depends on the shape, right? So depending on the geometry, dp by dx, the pressure gradient will change. This is for external flow. Similarly, for temperature, we can write functional form as x star, y star. Of course, it depends on Reynolds number and Prandtl number. And then since the u star depends on this dp by dx, so you have dp by dx dependence coming from there. Okay. So now, if we with all this discussion, if we go back to our definition of H, which was equal to which depends on del T by del Y at y equals 0, that means at the solid fluid interface, then we can try to non-dimensionalize this equation as well, and then see what happens. So Kf by L Dou T by dou Y can be written as, we have seen it before. T will be T infinity minus Ts, so that will be dou T star, and Y will be Y L times Y star. So this L and Y star, and you already have Ts minus T infinity. So what we see essentially is your H is essentially equal to, so H is equal to, this term will cancel out. H is equal to Kf by L and dou T star by dou Y star at Y star equals 0. Okay. So you can just rearrange it and then so that dou T star by dou Y star at Y star equals 0 depends on HL by Kf, which is again a dimensionless number called known as Nusselt number. Okay. Yeah. So this Nusselt number itself will then depend on, H. We know that H depends, if you go back, the temperature depends on this X star, Y star, Reynolds Prandtl, dP star by dx star. So your this thing will depend for a given shape. This X, it will only depend on X star, REL and Prandtl number. So we are talking about, when dP star by dx star is, if the shape is fixed, then this is no longer a variable. You have this, X star. Already you are doing the differentiation with respect to Y star. So this term and that goes away. So you have only three things that your Nusselt number will depend on. Okay. Now, if you talk about average Nusselt number, then this X star also goes away. So average Nusselt number only depends on. So this is very strong, conclusion from this analysis, that heat transfer coefficient, which is essentially, if you know heat transfer coefficient, you can do convection heat transfer calculations. And from this analysis, we could show that it just depends on Reynolds number and Prandtl. So this part we have already seen. The only thing is, for Prandtl number equals 1 and dP star by dx star equals 0, these two equations are exactly similar. So their solutions must be same. So under these conditions, what we can write is, Cf is your friction coefficient. So Cf times Reynolds number by 2 is equal to Nusselt number. This is since these two equations look similar, so the results of one equation should apply to another equation. So that is what we are trying to say here. Okay. So Cf should be equal to Reynolds. There should be some relation between this friction coefficient and heat transfer coefficient, and that is given by this analogous equation. Okay. So if you can solve, so from experimental point of view, this is very important. Heat transfer experiments may be easier to do. So if you know a Nusselt number for a given situation under these conditions, then you can actually find friction coefficient. So you don't have to do the experiments or measurements for friction coefficient. Okay. So a more general form of this analogy is available, known as Chilton Colburn analogy. According to that, if you define a Stanton number, or also known as modified Nusselt number, as Nu by Re Reynolds times Prandtl, then you can write the relationship between friction coefficient and modified Nusselt number or Stanton number. But this is valid only for the Prandtl number in the range of 0.6 to 60. Okay. So if you know one of the parameters, either if you know Nusselt number, then you can find friction coefficient. If you know friction coefficient, then you can find the Nusselt number. So this is very, very, very useful and powerful tool. Okay. So far we have done how to analyze the convection heat transfer coefficient, and with this we'll end our discussion on that part, and we'll now move on to particular cases like external convection heat transfer situation, and then we'll talk about internal, and then also we'll talk about other types of convection heat transfer, such as natural convection. So okay, so we'll end this with this part of the lecture with two practice problem. So thermal boundary condition, boundary layer thickness for oil is much larger. So oil Prandtl number is much greater than 1, and we have seen that delta by delta T goes with Prandtl raised to and where n is greater than 0. Okay. So based on this discussion, what can we say? The thermal boundary layer thickness should be much larger than velocity boundary layer thickness or smaller. That is the first part of the options. Second part is what is the reason for the same? Is it so because thermal transport is easier than momentum transport, or momentum transport is easier than, or we can say faster than thermal transport, and so on. So based on this, you can do based on the discussion that we just had, you can do this problem. The second one is again very simple problem. The average convection heat transfer coefficient for water flow, the thermal conductivity of water is given here. Over a steel plate, the thermal conductivity of steel plate is given here. So the average convection heat transfer coefficient is given as 100 watt per meter square Kelvin. So if you know that, then what should be your average Nusselt number at a distance 5 meter from a leading edge? So, right. So from here to here, if it is 5 meter, then what, for that, for this distance, from here to here, you have to find what will be your NU average. Okay. So you know that it's HL by K. The main task to know is which K you should use. Okay. So should it be solid K or should be fluid K? We just discussed it in this lecture, so you should be able to answer that as well, and then do the simple calculation to find what should be your average Nusselt number. Okay. So let us now move to convection. So in convection, we talk about 3 types of convection. First is the forced convection. Second is free or natural convection, and third is convection with phase change. In forced convection, what we essentially say is you have convection because of forced fluid. Fluid being forced to move over a surface. Okay. Yeah. So for example, if you have a hot plate that is at temperature Ts and you want to cool it, so what you may do is you may have a fan that will give you air at certain velocity and certain temperature, depending on your ambient temperature, and then you pass it over so that it cools this hot plate. So this is since you are assisting air, increasing the air velocity by installing a fan, or it could be water by you can install a pump and so on. So you are increasing U. So that gives you forced convection. Okay. This could be external, as in the case of flow over flat plate, or it could be flow past a sphere or a cylinder, or it could be your air, aeroplane wings and so on. These are the examples of external forced convection, where you have essentially your fluid can there is no obstruction as such for the boundary layer to grow. We'll talk a little bit more about it later. Okay. The second type in this case is internal forced convection, in which you pass fluid through an enclosed enclosed body like a cylinder, or it could be it could be other shape. So essentially, in such cases, what you do is you pass some fluid through it. So again, you are doing at U infinity, some T infinity, and the wall of this cylinder may be at some other temperature Ts. So there would be heat transfer between between this surface and the fluid, and surface may you can heat up surface, or you cool down surface by controlling this T infinity. And again, in this case also, it's a forced convection, so you will again have a fan or pump to assist to increase the fluid velocity. Okay. In the case of free or natural convection, what you will have is essentially, if you want to cool up this hot plate here, let us say this at Ts temperature, and then you have some ambient temperature is T infinity. So what will happen is the air, when it comes in contact with this surface, will heat up. So as the temperature increases, your density of air will decrease. So it will become lighter. So you will have essentially air will come from here, and then it will just rise up. Right. So it will rise up. So this will give you what is known as natural convection. Okay. Then the third type is associated with convection with phase change. So there are many examples where where phase change can happen. So for example, if you are boiling water in your kitchen, there is if it is boiling over, then there is there could be more heat transfer, because boiling actually increases the heat transfer because of energy associated with the phase change. Similarly, you could have cooling off, and then cooling can lead to condensation. There could be other types of phase changes as well. So convection associated with these phase changes are strong ways to enhance the heat transfer. So for example, and this is very important process industrially as well. In metallurgy, for example, you have quenching. You have to do quenching of steel and some other metals as well to achieve your high strength and so on. In the quenching process, you have water that when it comes in contact with very hot surface, it will boil over and then evaporate, and all those things happen. So that again will result in heat transfer. This is a very interesting area where there are different mechanism of heat transfer depending on with respect to time and so on. So in this course, however, unfortunately, we do not have time to cover this topic. We'll discuss about this forced convection and natural convection only. Okay. So we'll start with external forced convection. Then later we'll discuss about internal forced convection. Some examples of external forced convection we just saw are flow over flat plate, flow over curved surfaces like sphere, cylinder, airfoils, and so on. There are two characteristics of external forced convection that you should appreciate. The first one is boundary layer develops freely. So when we know that when you have flow over a flat plate, for example, there is a boundary layer development, and boundary layer will keep increasing as long your plate could be this large. There is no obstruction to this boundary layer growth. Okay, this is in contrast to internal flow, where if you have this flow through a cylinder, flow through a tube, then you can imagine that you will have boundary layer growth from this side as well, and then this side as well, like this. So in this case, the boundary layer development is not free. It does not develop freely. So there is some interaction, and there may be some obstruction and so on. Okay, that is the first aspect of this external force convection. Second one is that beyond this boundary layer, or in the bulk, the properties does not change significantly. The velocity or temperature does not change significantly. So here it remains at U infinity and T infinity. So it does not change significantly. Okay. So with that, let's talk about how do we essentially to solve the problem of convection heat transfer. We know that this Q double dash, the heat flux, can be written as H Ts minus T infinity. So very often your T infinity is fixed. Surface temperature is fixed for if you have constant temperature. If you are maintaining constant temperature at the solid surface, and to find this heat flux, all you need to do is find H. So essentially the problem of convection heat transfer is actually to determine H. Okay. So how do we determine H? Okay. So we can have a setup something like what is shown here. So let us say we want to know what is the convection heat transfer coefficient over this over this surface. What we can do is we can maintain this the surface temperature of this solid at Ts by heating it electrically. So we can record what is E and I, so that we know how much power it is taking, and to maintain this surface temperature, we have to supply the power that is equivalent to this heat loss. That heat loss is given by H times A times Ts minus T infinity, where H has to be the average heat transfer coefficient. So we can control this U infinity and T infinity by by changing fan capacity or whatever. So we know what is the velocity. Once you know that, once you do that, what you will do is we also want to optimize the experiment. So what we do is we do experiments in terms of dimensionless numbers. From our previous analysis, we know that Nusselt number is actually average Nusselt number is function of only Reynolds and Prandtl number. So what we'll do is we will select a fluid, let us say, which has a Prandtl number equals 1. Prandtl number is just a property of fluid. It does not depend on your flow conditions. I mean, as long as you don't consider the temperature dependence. So what we'll do is we'll conduct this experiment at different velocity, so that we know the REL. So and correspondingly we'll measure H from this equation. Once you will record IE, and from there you can calculate H. IE will be proportional to your H, right? So you will know H, and from this H you can calculate your Nusselt number, again average Nusselt number, NUL. So some value of REL you will get, and correspondingly you will measure HL, and from there you will calculate NUL. Okay. So once you collect all the data, you can plot it on a log plot. So log NUL here and log REL. What you will see is actually you will have something like this. Okay. So some deviations may be experimental errors, but it will give you more or less one straight line. So what it shows is that actually your Nusselt number is varies, depends on Reynolds and Prandtl in this form. So when you do log plot, this will be log of Nusselt number log C plus M log REL plus N log Prandtl, right? So for a given fluid, your this N generally does not change with the fluid. So these two terms are constant. So that will come in the intercept, whatever is the intercept, that will be the sum of these two terms, and the slope of this line will give you essentially the power m. So now you can change the fluid from PR with Prandtl number 1 to Prandtl 1 PR1 to PR2, PR3, and so on. So all these lines should be parallel, and you can in fact go one step further and probably plot this log of NUL by Prandtl raised to n with respect to log REL. So this should now converts all the data to single line. So you will have just one line, and from there the slope of that line will be equal to slope will be m, and if you do the intercept, that will be log C. Okay, so this is how you will typically go about to measure the convection heat transfer coefficient, actually present it in the form of this Nusselt number correlation. So most of the correlations that you will see from now on are actually will be given in terms of Nusselt number. Okay, so this is the empirical empirical equations will be of this form. Of course, there are very few special cases where one can actually solve the energy balance equation, and then actually find the temperature as temperature as function of x and all those things, and temperature profile in the boundary layer, and from there one can calculate the convection heat transfer coefficient, right? And so on. This can only be done even with that too with a lot of effort for flow over flat plate, and only for laminar flow, and then again for some Prandtl number greater than some 0.6 or something. So the correlations for convection heat transfer coefficient has this form. In these correlations, constant fluid property has to be assumed, and you know that the fluid temperature changes, so you can have the Ts here and T infinity here. Fluid temperature changes from here to here. It goes from Ts to T infinity, and thermal properties actually change with temperature as well. So thermal conductivity, for example, change with temperature, and viscosity may change with temperature, and so on. So what we typically do is we take all the properties at what we call as film temperature, which is Tf equals Ts plus T infinity by 2. Okay. So if you go to the textbook has it will have table for thermophysical properties. So and in that it will vary with temperature. So it will have 300, 350, 400, 450, and so on. And then you will have some K value, some 0.1, 0.2, or for gases it generally increases with 0.25, and so on. For gases it increases with temperature, the thermal conductivity. Again, viscosity will vary and so on. So for your given condition, you should not take the properties at if T infinity is 300 Kelvin and this is 600 Kelvin. So you should not take either on 300 or on 600. You should rather take at an average 300 plus 600 by 2, right? So TF will be your 450 Kelvin. So at that temperature, you should take all the thermophysical properties. You should be careful. Sometimes they would actually when there is some correlations, they will tell you that okay, you can take at TS temperature, then you can take at TS temperature. So actually it depends on how that person derived that correlation. They may have taken the film temperature, or they may have taken surface temperature, so you have to be careful. Okay. So now the correlations, we'll just go directly to the correlations. We are not going to develop the correlations using boundary layer, trying to solve the boundary layer equations. So for convection convective heat transfer, we are talking about this laminar flow. Nusselt number is given by Hx x by k, and that is the correlation of it is of the same form. Nu is form of C Re power m P R power n. So m is equal to half, n is equal to 1 by 3, C is 0.332. This correlation is valid only if your Prandtl number is greater than 0.6, which is true for some gases and oils and things like that. For liquid metals, your Prandtl number is much smaller than 1. So for Prandtl number less than 0.05, you can use this correlation, which is Nusselt number equals 0.565 times. Here m is equal to n is equal to 0.5. The product of Reynolds and Prandtl number is also known as Peclet number. So this is the correlation that you can use if your Prandtl number is less than 0.05. Okay. Then for turbulent flow, what you can do is you can take Nusselt number so here you will have C is 0.0296, Reynolds is 0.8, and Prandtl is to 1 by 3. This is valid only if your Prandtl number is between 0.6 and 60. I think the transition for flat plate is at 5 into 10 raised to 5 Reynolds number. Okay. So with once we but again recall that, note that this Nusselt numbers are local Nusselt number, not the average Nusselt number. Very often you will need the average Nusselt number. So if you know the correlation for NUX, then NUX is equal to your Hx local convection heat transfer coefficient times x by k. So Hx is then equal to Nusselt numbers x times k divided by x. So average Hx will be 1 by x integral of this NUX k by x and then dx. So you have to do this integration to find what will be your average convection heat transfer coefficient. Okay, and in fact from there, now once you know that, you can also find an equation for an average Nusselt number, which will be Hx average times x by k. Okay. So this is the way you should avoid directly taking the average of Nusselt number. You have to first take the average of Hx and then you go to Nusselt numbers. Okay. On the same line, so with that, we'll continue our discussion on this external force convection in the next lecture. For now, let us end with this practice problem. So where your Nusselt number is given by NUX is 0.332, Reynolds raised to half, Prandtl is 1 by 3. So you are given the local Nusselt number. How can you find from there the convection heat transfer? How does the convection heat transfer coefficient? Coefficient should be here. Convection heat transfer coefficient vary with x. So does Hx vary with 1 by x? Hx vary with x raised to minus 0.5. And then here you are talking about average Hx, and here you are again talking about average Hx. So which of these are correct? Okay, there may be more than one correct options. So you have to just make sure that your concept of Nusselt number to to calculate convection heat transfer coefficient, and hence the average convection heat transfer coefficient both you could understand and can do. Okay, so you can spend few minutes to complete this. Okay, with that, thank you for your attention.